Hi everyone. So it's my pleasure today to welcome Jérémy Ledent from the University of Strathclyde. Sorry, we will be talking about knowledge and topology. Thanks.
Okay, so I will share my screen. And can I move the slides? No. Okay. So yeah, I'm going to talk about some work I did with Eric and Sergio Rasbom from about knowledge and topology using simplicial complexes. So last week there was a talk by Alexandru Baltag about knowledge and topology too. But he was talking about topology in terms of open sets and this kind of topology. Here it will be more algebraic topology. Looking at simplicial complexes and those kinds of shapes. You're welcome to interrupt to ask questions during the talk if you want. And so I will give a brief overview of the themes I'm going to talk about. So first there will be epistemic logic, which is the modal logic of knowledge. We are going to talk about agents that can know things about the world and how do we reason about this knowledge. And epistemic logic has been used to study distributed computing by Halpern and Moses and other people since then. And they used it to model the knowledge of processes that are communicating in a computational setting. And another approach to study the same problems is the one of Herli and Shavit and other people who used combinatorial topology, so simplicial complexes and those kinds of tools to study distributed computing. So the story I'm going to tell is first a direct link between epistemic logic and topology that I will explain. We call it simplicial models for epistemic logic. And this has uses for distributed computing where we can kind of combine those two approaches, the logical one and the topological one. So I will now introduce those three fields. And I will start with a little story about epistemic logic. So this is called the two generals problem. We have two generals, A and B. Maybe let's call them Alice and Bob. And they want to attack some fortress in the middle here. And to do that, they know for sure that they have to attack simultaneously. So if they attack at the same time, they know for sure that they will succeed. And they also know that if only one of them attacks, they will lose the battle. So they have to attack at the same time. And so they need to coordinate, and to do that they send messages back and forth. But the messengers might be captured by the enemy, and if that happens, the message is never received. So how can they coordinate this attack, and how long will it take? So let's imagine that maybe Alice is the highest grade in the military, and she gets to decide the time, and she will send a message to Bob saying, "We attack at dawn." And let's suppose that the message arrives. So now both Alice and Bob, they know that the attack should happen at dawn. But there is still a problem, because from the point of view of Alice, maybe this message was not received. And if that is the case, then Bob doesn't know when to attack. So from the point of view of Alice, the attack cannot occur right now. She needs more information than that. So let's say that now Bob will send an acknowledgement to Alice to tell her that the message was received, and we can proceed with the attack. So can they decide to attack now? So they both know that the attack should happen at dawn, and they both know that Bob received the message, but they still cannot attack. Why? Because from the point of view of Bob, maybe this message, the acknowledgement, was not received. And without the acknowledgement, as I said before, Alice will not attack. So if the acknowledgement is not received, Alice will not attack, and so Bob cannot attack right now. He needs more information. And so we could try to keep going, send more messages back and forth, more acknowledgements, but as you can imagine, we will never reach absolute certainty that they are able to coordinate the attack. Because what we do not have is called common knowledge. Common knowledge is I know that you know that I know that you know, back and forth an infinite number of times. And and you cannot reach this kind of knowledge just by sending those messages. Even if all messages arrive, there is still this possibility that maybe the message didn't arrive, and so there is a hypothetical world where the coordinated attack cannot occur. So let's try to model this with this little graph here. So this is the initial situation before any message is sent. And here we have one vertex representing Bob, who is just awaiting orders. And there are two vertices for Alice representing different possibilities, different possible worlds. So the situation I was describing is this edge here, which is, I will call the world W, where Alice wants to attack at dawn. But from the point of view of Bob, there could be another world W prime, where this time Alice wants to attack at noon. And so this vertex here, representing Bob, is shared by those two worlds, those two edges. And that means that the B doesn't know which is the real world. And so let's look at what happens when Alice sends a message to Bob in this situation. So here we have two possible worlds. And when Alice sends a message, now we have four possibilities, because in both cases, the message can be received or it can be lost. And so, for example, if Alice wanted to attack at dawn, I will put some colors here. So if we are in this world here on the right, there are two possibilities. Either the message is received and we get to this world here in green, or to this one where the message is lost. And as you can see, this vertex here labeled with Alice doesn't know whether the message was received or lost. So this vertex belongs to both edges. And the same happens on the left side, where this original world here is split into two worlds, whether the message is lost or received. And we can keep going. So this is the after Alice sends a message to Bob, and now if Bob sends an acknowledgement, we get some new world, whether the message is lost or received. But as you can see, this graph remains connected. And this is something we can prove, that after any number of messages sent, the graph of all possible worlds is always connected. And what that means is, if all messages are always received, we will get into this world W here at the extremity. But what happens is that here B is uncertain whether we are in the world W or maybe in this world. And now in this possibility, Alice is uncertain of whether we are in this world or in the other. And so we can walk around this path until we reach this world W prime, where here this is in the left part, so Alice now wants to attack at noon. And so the connectivity says that there will always be some possibility, some sequence of hypothetical worlds where you end up in a situation where Alice wants to attack at noon instead of dawn. And so this can be used to show that the impossibility of solving this two generals problem. So this was an instance of a distributed computing task called consensus, where some agents are trying to agree on some common value. So let's look at the more general setting of distributed computing. So we have some number of computers, of processes, that here are represented as colors. So each one has its own identity. Before it was just Alice and Bob, but you can have more. You can have 5 agents participating in the task. And they are all given in the beginning an input value. Here the input is a natural number. In my example, it was attack at dawn or attack at noon. So you have an input in the beginning, and you want to communicate with the others to transmit information. So to do that, maybe you can send messages, as in my example, and this could be a faulty network where maybe the messages can get lost. Or you could have other communication models, maybe a shared memory, where you have this memory and all the processes can read and write information on it, and so they exchange information by doing that. And they could have some more advanced communication primitives that are available in computers. And in general, we call it a task where the processes, they communicate in some way. And at the end, they want to decide an output value. So here, each process has decided to return a value after the end of communication. And this decision is local. So with its local information, the computer decides a value. And this is equivalent to choosing to attack at dawn or at noon in my previous example. And the task specification here is global. So it takes into account all the input values of all the processes, and you look at all the output values, and you decide whether this is a good execution or a bad execution. And here, for consensus, they all decide the same value, so this would be a correct execution of the task. So this is how you specify what you want the processes to achieve. And as in the 2 generals example, what we want to do usually is to prove impossibility results. We want to show that some tasks are impossible to solve in various computational models. So you might know about computability in the standard setting of Turing machines and this kind of thing. Here, this is very different. First, because we have many different computational models, maybe messages or shared memory or more powerful ones, and they are not equivalent. So we have to study all the models separately. We don't have a universal one like Turing machines. And the other difference is that impossibility here comes from a lack of information. You have to deal with the failures, the messages that get lost, and this kind of thing. It's not a problem of computational power. It's a problem of dealing with information and lack of information. And so several methods have been used in the literature to show impossibility results. I mentioned those 2 in the beginning, and those are the ones I will focus on, combinatorial topology and epistemic logic. And this one is a very famous one, the first impossibility result that was proven. All right, so let me talk a bit about epistemic logic. So epistemic logic is the formal study of how do you reason about knowledge. So we will have logical formulas that say some agent knows some fact about the world. And many variants of knowledge have been studied. There is also belief, understanding. There are some probabilistic knowledge. Last week, Alexandru was talking about learning, and there are many things. And here I will take just the most basic one, which is just knowledge, knowing with absolute certainty that something is true. And this is kind of the most easy one and the most well-defined one, the better studied. So I want to keep it simple to focus on the topology. So the syntax of epistemic logic formulas is like this. You have atomic propositions, you have negation, conjunction, and you can define from them the other propositional connectives. And the important one is this one called the knowledge operator. So here you have this little a, which is an agent. It belongs to some finite set of agents that we fix in the beginning. And this agent can know a formula. So here, for example, this formula is read. Agent A knows that agent B doesn't know that the formula phi is true. And in distributed computing, the agents are going to correspond to the processes that are trying to solve a task. And the atomic propositions will be facts about the system. So that we can say the process knows that some other process received a message. This kind of formula we can express and study. So to give a semantics, a meaning to those formulas, we need, so the standard way, as done in the literature for many years, is to use Kripke models. And a Kripke model consists of a set of possible worlds, W. Then for every agent, we have an equivalence relation on the set of possible worlds. And this is called the Indistinguishability Relation. It tells you that the agent A here cannot distinguish between two worlds. And finally, we have this labeling function, which tells you in each world a set of atomic propositions, which we consider to be the ones that are true in this world. And so different worlds can have different sets of true atomic propositions. So for example, with once again the two generals, if we want to model this in using a Kripke model, we will have two worlds, W1 and W2, and they correspond to the world where Alice wants to attack at dawn and the world where Alice wants to attack at noon. And this is described here by the labeling function, which says that in world W1, the attack should happen at dawn, and in world W2, it should happen at noon. And so dawn and noon are the two atomic propositions. The agents are Alice and Bob. And here we have the indistinguishability relation that says that agent B, so Bob, cannot distinguish between those two worlds. And so if you remember how I was drawing it before, I had this picture with two edges. And so this vertex in the middle represents the local state of Bob, and those two edges represent the worlds W1 and W2. And so you see there is some kind of duality here, where the edges became just vertices here, and this vertex in the middle expressing that Bob cannot distinguish between the worlds, it became here an edge, a relation between the worlds. So this picture will come back later, but for now let's talk about those models like this. Once we have a Kripke model, we can define the truth of a formula, the satisfiability of a formula, which is written like this. So this says that in the model M and in the world W of the model M, the formula phi is true. And to define this, first we do the usual thing of propositional logic. So an atomic proposition is true if it is in the labeling of the world. Negation is true if the formula is not true and the conjunction is an AND. So this is very simple. And the important part is the knowledge operator. So when does an agent know some formula? Well, so in the world W, so the condition is for every other world W prime, which is indistinguishable from W, from the point of view of agent A, the formula has to be true in the world W prime. What this says is, you know that some formula is true when this formula is true in every possible world which is indistinguishable from the current one. So you have a set of worlds that you consider to be possible, and to know something means that it has to be true in every possible world from your point of view. So to look at the example, let me just draw the picture again. It was like this. W1 and W2 are indistinguishable by agent B. And so in the world W1, so we are in this world, the agent A knows that, and this one is dawn and this one is noon. So from the point of view of agent A here in world W1, the only world which is indistinguishable is W1 itself. So we just stay here and we can verify that dawn is true in this world. But for the agent B, this is not the case because we also have to check the world W2 where the formula dawn is not true. So from the agent B doesn't know that the attack happens at dawn, which is what intuitively we would say in this situation with Alice and Bob. Alice didn't send a message yet, so Bob doesn't know that the attack should happen at dawn. Okay, so now what I'm going to do is to present a different kind of model for epistemic logic, which is based on simplicial complexes. So now you will see the topology occur. So just to, as a reminder and to set notation, an abstract simplicial complex is a pair of vertices and a set of simplexes, which are subsets of the vertices. So we have some vertices, and this is, you can view it as a generalization of the notion of graphs. So you have some vertices, and then you have some subsets. And if I have this two-element subset here, in my set of simplexes, I will draw it as an edge. So you can have several edges. So that's why this is a generalization of graphs. You can have several edges, but then you can also have simplexes with three elements. So if we take these three vertices and put them in a simplex, I will draw this as a triangle, which is filled here. And so, as you see, this gives you some kind of combinatorial version of topological spaces. So you can triangulate a space and view it as a simplicial complex. Then what I'm going to do is take a simplicial complex and add colors to the vertices. And the colors here are going to be the agents. So we have a map that associates every vertex with an agent. And here they are represented as three colors. So as you can see, this is an example of a chromatic simplicial complex of dimension 2, where we have those triangles, and pure here means that I have only triangles. I don't have an extra edge, for example, which would be of a different dimension. So here everything is of dimension 2, and this is called pure. And finally, I have my pure simplicial complex of some dimension n, and I will add some labeling to say in each vertex which atomic propositions are true. And this is implicitly what I was doing there with this picture, where here Alice wants to attack at noon, and this is this one is an atomic proposition, and this one is an atomic proposition. And this one I could just remove, or it could also be an atomic proposition, but it's not a very interesting one. But so we have vertices with a color representing the agent and an atomic proposition representing facts that are true in this world. Let's do another example with three agents this time, and as you will see, this will get more interesting topologically. So now let's consider we have a deck of 4 cards, 1, 2, 3, 4, and we have 3 agents called ABC. And we give 1 card to each agent, and the remaining card stays hidden. And we will try to model the knowledge of all the agents about the cards in this initial situation. So one possible world is represented by this triangle. So now we have 3 agents, and so the dimension will be 2. That's why we have triangles. And here, this triangle, if you look at the vertices, they have a color representing the agents. So here the purple is the agent A, the blue is agent B, and the yellow is agent C. And we have the numbers 1, 2, 3 that represent the card of each agent. Another possible way to deal the cards is this one, where this time agent A received the card number 4. And so this gives another triangle with those 2 vertices are shared, because from the point of view of the agents B and C, they are the exact same situation. They only know their own card. But now we have a new vertex for agent A with the card number 4. And here the fact that those 2 triangles are glued together, this is what expresses the fact that agents B and C cannot distinguish between those 2 worlds. And so we can keep doing this. I don't put the bubbles because all the information is there. And if we put all the worlds together, what you get is a triangulated torus, where each individual triangle is a possible world, a possible dealing of the cards to the agents. And the topology of the torus is what will give information about the knowledge. So you can move from triangle to triangle and look at formulas saying, I know that you know that something is true. And this topology will give information about the knowledge of the agents. So this is a very nice idea that hasn't been studied by epistemic logicians. They used those cryptographs where, in fact, there was all this hidden topological information behind those models. So we can define the validity relation, the truth of a formula in a simplicial model. So this is exactly as before, but now this X here, the world, is a facet of the simplicial complex. It's a maximal world, a triangle if we have 3 agents. And the definition is the same as before for the propositional logic. And for the knowledge operator, what we do is we say that agent A knows some formula if this formula is true in every world Y, which is a facet, and which shares this vertex of color A with the original facet. So this is just translating the indistinguishability idea between worlds. So if a vertex belongs to 2 different facets, then the agent cannot distinguish the 2 worlds. This is the meaning of gluing the triangles together.
I have a question.
And so here I just remind the definition. And let's look at this example. So this is not the full torus. This is just a toy example where we have some worlds.
Jeremy, someone has a question.
Yes?
Regarding the torus in the 2 past slide, what does the homology of this complex say about the knowledge?
So this is a very difficult question, and we are still trying to investigate these kinds of questions. Of course, this is the interesting part, trying to link together the topology and the logic. I will come back to it towards the end of the talk, but I don't have a very good answer. This is still a work in progress, and we have to figure out good connections between logic there.
Okay.
But I'm convinced that there should be something. But
Yeah,
this is a very good question.
It's interesting because the homology, the simplex reflects knowledge. So the homology must tell you something about the all possible words you are considering, no? Well, I don't know. It's
Yes, completely. There should be things here, and I will give little hints, but I will not give a very good complete answer to this question because it's a difficult one.
Yeah. Okay.
But
Thank you.
that's a very good question. This is where the important part of the talk is.
Okay.
So let's do this little example here, just to see what the validity relation looks like. So I claim that this formula here is true in the world X of this model. So how do we check it? So we are in this world X, and this formula starts with A knows. So the agent A is the purple one here, so this vertex. And so first we have to look at all the worlds that are sharing this vertex. So from the point of view of A, we could be in X, but we could also be in Y or in Z. So now we have to check this formula here inside in these three worlds. And so now this has a B nose. So we look at agent B, which is the blue one, and we have to look at all the possible worlds that are that B considers possible in this situation. So there will also be this one and this one and this one. And so now we have to check this formula in all the yellow region here. And this says that the value of C is different from 1, which is correct because C is the yellow agent, and in all possible cases, the value is different from 1. So this is how you can interpret formulas on these models. And as you can see, iterating knowledge, I know that you know that I know, this is making you work on the model and explore the topology from neighbor simplex to neighbor simplex. So what's the link exactly between those models that I was talking about right now and the models I presented before, the Kripke models? Well, we showed that we have an equivalence of categories between the structures, which means that this is basically the exact same information, but said in a different language. And so what this means is we can go from a simplicial model to a Kripke model. This is very easy. This is the intuition that I gave. The triangles are the worlds. So 3 triangles will give 3 worlds. And then the indistinguishability relation is given by sharing a vertex. Here there is a shared vertex between W2 and W3, and so the agent B cannot distinguish between W2 and W3. The more interesting part is that we can go in the other direction. So given any Kripke model, which is just a one-dimensional graph, there is actually enough information to recompute the topology of the model and to rebuild the whole simplicial complex that represents this model. So yeah, these two kinds of models, the ones that epistemic logicians have been studying for many years, and the ones that we introduced, they are really the same thing. So this is very interesting because this says that if you are interested in epistemic logic, well, there is some hidden topological information in the model that you didn't know about and that could be very useful to prove facts about the formulas. And this is also interesting from the point of view of distributed computing because those models here on the left, they have been used to prove things about distributed computing. And what this tells you is that you can just interpret epistemic logic formulas on those models for free. You don't need to add any extra information. The model contains already everything you need to reason about the knowledge. All right, so this is a very important theorem that we proved. And in the next part, I will try to extend this theorem and to try to break this equivalence. So now we have two kinds of models and they are actually the same. And now what I want to do is I want to remove those assumptions about the topology. I want to remove the assumptions that models have to be pure and the assumption that they have to be of dimension n. Try to have a bigger kind of model. that will be more expressive than the Kripke models. So I want to do more, to be guided by topology, to generalize the models and see what it means from a logic perspective. So yeah, we want to generalize this notion. And of course, the most obvious thing to do is to remove this condition that models have to be pure. And so we could have models that look like this, where we have this triangle in the middle, but we also have worlds that are just edges, and we have worlds that are isolated vertices. And this is used in distributed computing to model systems where the processes can crash. So for example, this is an execution where all the processes were executed without problems. But here, this is an execution where the yellow process crashed during the execution, so now it doesn't exist anymore. And so there are some worlds where some agents are missing. And this is a very, very simple idea, but it hasn't been very much studied from an epistemic logic perspective. And I think this formalism is the right one to study this. What we did is, as those we had an equivalence with the pure models and the Kripke models, and now we are extending the simplicial models. And what we did is we can catch up with the Kripke models to find an equivalent class and to express in more standard terms for epistemic logicians what those models are about. And the more important part that I'm going to talk about is we also axiomatize the logic. This new class of models gives a new logic, and we try to understand what are the new assumptions about this logic and what it looks like. So this is still the same definition as before, but now we just assume that the model might not be pure. So let's look at a tiny example just to see what happens. And I will remove the colors just to be able to read directly inside the vertex what the agent is. And the atomic proposition P here is going to be true only in X1. So we can look at some formulas. So these ones are very, very simple. So for example, here, agent B in world X1 doesn't know P. Well, because from the point of view of agent B, there are two possible worlds. It could be X1 or it could be X2. And P is true only in X1. So B doesn't know that P is true. So this is just as before. Okay, we can do some conjunction. And this is the important one. I claim that in the world X2, agent A knows that P is true. So as you can see in the world X2, agent A doesn't even exist. So what does it mean to know something when you are just not there? It's not very clear. It seems like an ill-formed formula that shouldn't be true. It shouldn't be false. So why do I claim that this is true? So this is just guided by this definition that we had, where here we say for every facet that shares a vertex with X2, we should have some condition. And since there is no vertex here, there is no facet, and this for all is vacuously true. So okay, this seems like a weird formula, but I claim that it should be true in this world. And here, last example, in X1, I say that agent B knows that A knows P. Why? Because from the point of view of agent B, there are two possible worlds, and I already checked for both of them that A knows P, and so this one is satisfied. All right, so what does it say? So the important part was this one where an agent which doesn't exist basically knows everything. And in fact, we can use this as a definition to define what it means to be dead or to be alive in this model. And this is defined. This is not something that we have to add in the logic. This is just a shorthand for Ka false. Just like you can write phi or psi, as a shorthand for not phi and not psi, as you know in propositional logic. So this is the same idea. We just define a new operator from the ones we already have. And you can check that this corresponds to what we want. So an agent is alive in a world if the agent belongs to the vertices of that world. And then we can play with these semantics and have some formulas. So the dead agents, we can prove that they know everything. So since they know false, and false implies anything, then we can show that. We can show that alive agents, they know that they are alive. This is an interesting fact about those models. And we can show that alive agents satisfy axiom T. This is called the axiom of truth. This is usually in epistemic logic, you have only this part, which says that if you know something, then this formula has to be true. And now we don't have that, because we have dead agents that can know false. But we have something very close, which is that alive agents, if they know something, then this is true. So we recover a little bit of the old epistemic logic axioms. All right, so this was about removing the assumptions that models are pure, but we can go beyond. We can generalize even more. And you might know about simplicial sets that generalize simplicial complexes, where you define, so here, if you look just at this part here, this is a graph where you have a set of edges, a set of vertices, and you have a source and target maps. But this is a graph that can have loops, and that can have several edges between two vertices. And this is not allowed with simplicial complexes, but this is allowed with this presentation of graphs. And here we do the same, but we also have a set of triangles that have three edges and more. And so what we can do with these simplicial sets is, for example, this model here, where we have two triangles, and they share both the vertex labeled by A and the vertex labeled by B. But the edges are not shared, so you have this little hole in the middle. And in terms of logic, this is something that we can find in many situations, where you have two possible worlds, and the agents, individually, they cannot distinguish between the two worlds. The agent A cannot distinguish between the world, and the agent B cannot distinguish between the world. But if they put their knowledge together, and this is represented by the edge AB, then this edge belongs only to W1 and not to W2. So if the agents put their knowledge together, they are able to distinguish the worlds. And for example, this happens in cryptography, where we could imagine that agent A has some hidden message, and agent B has the secret key to see the message. And individually, they are not able to see the contents of the message, but if they put together the message and the key, then they are able to see in which world they exist. So this is something this is work in progress. And this is another way that we can generalize the models and see what logics comes from it. And this allows for better expressivity to express more situations. All right. And finally, I want to talk a little bit more about the applications to distributed computing. So let me summarize very quickly this approach of Hurley and others that have been using simplicial complexes to study distributed systems. So first, you have an input complex, which is a structure that describes the knowledge of all the agents at the beginning of the computation. I had the same with Alice and Bob and the generals at the beginning. We had the input situation, and then it evolves when we send messages. You can specify the task with some kind of map between simplicial complexes, and you can also specify the computation, the execution of the model. So from the input model, you exchange messages, and then you get a new model with more worlds and maybe a different topology. And this model has acquired new knowledge. And then solving the task, the Hurley and others showed that to solve a task, there needs to exist a simplicial map from the protocol complex to the output complex that satisfies some condition about this diagram. So you should have some kind of inclusion between this map and this one. And so the goal to show that a task is impossible to solve is to show that there does not exist this simplicial map. So we went from a computational question, is it possible to solve a task, to a topological question, which is, does there exist a simplicial map from the protocol complex to the output complex? And they have been using this idea to use topological invariance to prove impossibility. For example, here this one is disconnected and this one is connected, and you can reason about that, and this will tell you that there cannot exist a simplicial map that satisfies the conditions. So using this very nice idea, they have been using topological invariance to express that a task is not solvable. And what I will do is use the same idea, because those things are already simplicial models. We can interpret logical formulas on them. And I will try to find a logical invariance instead of a topological invariant. And this is the idea that we have been using. And so the theorem that we use is called the knowledge gain. And it says that if we have a simplicial map between simplicial models, then a simplicial map cannot acquire new information. If some formula phi is true after applying the map, then it was already true before. So if I go back to this one, what this tells you is every formula that is true here was already true before. And usually this is a formula about knowledge. So this says that in order to solve a task, starting from the input complex, you have to acquire knowledge by going through this map. So here you communicate and you acquire knowledge, but then the map here cannot acquire new knowledge. It cannot. You cannot learn things just by deciding an output value. And so here, what we will try to do is this. We assume by contradiction that this map exists, this delta, and we want to find some formula that expresses the knowledge which is necessary to solve the task. And we will show that phi is true everywhere in the output and is false at least one world of the protocol model. And if we do that, thanks to this knowledge gain lemma, we get a contradiction. And so the important part here is that we get a formula, which is an epistemic logic formula. It talks about the knowledge of the processes. And this formula is telling you what knowledge is necessary to solve the task and that you cannot acquire by communicating. So for the generals with Alice and Bob, this is called a common knowledge. I mentioned it in the beginning, that in order to solve the problem with the generals, you need to have common knowledge, which is an infinite sequence of I know that you know that I know that you know. And by communicating, they can only get a finite sequence of knowledge like this. So they can never reach common knowledge. And for other tasks, we can find different formulas that explain why the task is not solvable. So we did that with several tasks. So for consensus, this is about common knowledge. there is the approximate agreement task, which is a weaker version of consensus. And this time, this is iterated knowledge. So this is just a finite sequence of I know that you know that I know. And we showed that in order to get a close enough approximation of consensus, you need to have enough iterated knowledge. And then we got stuck on this set agreement task, which is another cousin of the consensus task. And the interesting part is that we know from combinatorial topology that to prove impossibility of this task, we need to study the k-connectivity of k-connectedness of the model. And so this uses higher dimensional topology, where the common knowledge corresponds to connectedness. So this is one dimensional. We can do it on graphs. And this is already well understood even for Kripke models. But here we really need the higher dimensional topology in order to do set agreement. And so this is interesting this is where we will see how the topology influences the logic. And here we didn't manage, we managed to do it, but the formula is not very interesting. More recently, there is this very nice paper by some Japanese people who used our setting, and they managed to find a formula for set agreement. And this formula is very complicated. We don't really understand what it says precisely yet, but this is somehow encoding into the formula the proof of Sperner's lemma, which is related to this k-connectivity issue. And so this shows that the logic is able to catch up with topology and to express those higher dimensional connectivity issues. And we also have a negative result where we showed that for this little task called equality negation, there is no formula at all that can work. So this shows some limitations of our framework. And so finally, some research directions. So in this talk, I only used this knowledge operator, Ka-phi. And in fact, there is another operator which is going to be very important for the future, which is called distributed knowledge. And this is talking about a set of agents. So you could write there is distributed knowledge among agents A and B that some formula phi is true. And this is something I mentioned a little bit, if you remember, when there was this picture with the two triangles that are sharing vertices, but not the edge. So here we have the agents A and B here, and individually they do not have. There is no knowledge of anything between those two worlds individually, but the distributed knowledge is what allows you to look at the edge and to see this hole in the middle. And so this distributed knowledge operator will be very important to study further the higher dimensional topology. There is common distributed knowledge, which combines both distributed knowledge and common knowledge. So this is some infinitary formula that does both common knowledge and distributed. And this is related to the question that someone asked about the homology. Here I talk about k-connectedness. So there is this correspondence is very well understood between consensus, connectedness, and common knowledge. And this is one-dimensional. But then there is this set agreement task that I mentioned a few slides before, which we know is related to k-connectedness. And then the logic is not clear yet. So what I think is that maybe we need to introduce a new logical operator whose semantics would be about the higher dimensional connectedness of the model. And this is something I would really like to understand. How can you logically express this? We have a little bit of a hint in the paper of the Japanese people with this proof of Perner's lemma encoded in a logical formula. But I would like to find someone better, maybe. And finally, these are kind of really mathematical open questions, no link with distributed computing. How do we really connect the topology and the logic? What topological properties can we characterize with logical formulas? And here are some examples of the kind of questions we could ask. They are maybe quite ambitious. Maybe we could have some smaller things. But yeah, for example, can you find a formula which is true exactly when the model is a pseudo-manifold? Can you find an axiomatization of the collapsible simplicial models? This is some kind of combinatorial version of contractible. It's stronger than contractibility, but this is combinatorial. So maybe this one could be easier. And when you subdivide a simplicial complex, the topology is preserved. So there should be some formulas that are preserved. And things like iterated knowledge, when you say A knows that B knows that C knows, this is looking at how many steps you take to go into the model. So this is not preserved under subdivision. But things like common knowledge, having common knowledge among a set of agents, this is related to connectedness. So this is preserved by subdivision. And I would like to try to understand which properties of the logic are preserved or not by those kinds of transformations. And this is all. Thank you for listening.
Thank you, Jeremy. Thank you for this very nice talk. Are there any questions?
I have a question.
Yeah?
Yes.
Could you go back one more slide?
Yeah. This one?
So the common distributed knowledge, that's like saying that like this like group A knows something and also group B knows something?
So this is saying that some group knows that some other group knows that some other group knows, blah, blah, blah.
Okay. Okay, I see.
Infinitely, an infinite formula like this, where you iterate, yeah. So this is why here you have this, which is a set of sets of agents. And so you would it looks like this. It looks like distributed knowledge among some set B1 of distributed knowledge among some set B2 of something, and all those sets B1 and B2, they belong to this beta. Right? So you have a set of sets of agents, and it tells you which sets are allowed to be iterated.
How do you know the order?
Yes, so this is a big conjunction about with every possible set here.
Okay.
Yeah. So yeah.
Thank you.
If you know about common knowledge, it works the same. It's a bit more simple, but yeah, this is the same idea. It's iterating every possible formula that you can write of any possible length. So it seems complicated, but it actually subsumes everything that we care about. So this is a very nice operator.
Okay.
Thank you. Other questions?
Yeah. The presimplicial sets are precisely the regular triangulated spaces of Kozlov?
I don't. So you are talking about this slide? I
Yeah.
don't know about the regular spaces of Koslov.
Because I think I mean, a presimplicial set is just a simplicial complex allowing multiple simplices on a set of vertices. Is that true?
I am not sure, but so this is this is a well understood notion from algebraic topology. It's actually very general. So this picture is simple, but it can get quite complicated. You can do really many things. Maybe it's equivalent to what you are saying, but I'm not completely sure.
Okay.
I would add probably that yes, you can produce a presimplicial set out of any topological space without triangulation. I mean, some topological spaces, they cannot be triangulated, and you couldn't do that either with a simplicial complex. I mean, so presimplicial set already is quite general. Of course, general simplicial sets with degeneracies, there's a little more in some sense. I mean, but already, if you think about how would you go from any topological space, even a very pathological one, and produce something which looks like a mixture of triangles, etc., and so on. Simplicial complexes, you need to be triangulated. You need to have a topological space which can be triangulated. Whereas presimplicial sets, you don't need that. I mean, yeah.
Okay. Thank you.
Are there other questions? No? Okay, so I think we can thank the speaker and the audience, of course. And thank you all. Have a nice weekend.
Thank you.
Yeah.